For this video, let us try to discuss and illustrate the length of a certain vector. We have here a vector x with its components, and they are still, this is still on R2. Now, the length of vector is also synonymous to the norm of a vector, because both of them talks about the size or the length of the vector. Specifically, the length of the vector refers to the magnitude or the distance of the said vector. Let's say this vector, the distance of that from the origin, while the norm is a more general mathematical term that measures size or length of a vector. Now, I'm trying to illustrate this like this because there are two interchangeable notations for the length of a vector. If we talk about the vector x, it can be denoted as this. Okay, as we know, it looks like an absolute value notation because generally the absolute value of a certain number is its distance from 0, right? The absolute value of 3 is the distance of 3 from 0. This is how we illustrate the length of the vector, but the norm also uses this notation. So basically, for some references, they are interchangeable, but they mean the same thing. They mean the length of the certain vector or the size of the said vector. So we might be using this in the next few videos, or this one here. We just need to use them properly to illustrate really what we mean. Now, for this certain vector, vector x, with the components x sub 1 and x sub 2 in R2, its norm or the length is denoted as this. So let me use this notation. The norm or the length of the vector is denoted as the square root of the sum of the squares of its components. So since we only have here in R2 as actually the square of x sub 1 plus the square of x sub 2. This is the norm or the length of the vector. Again, interchangeable. Others would like to use this one here. Okay, so just for the reference of that. Of course, if this is not in R2, if it's in R to the power of n, if it's in R to the power of n, this would mean that the norm of x is actually equal to, or let me write it here, equal to the square root of the components until x sub n. But of course, we are on R2, and this is why we are discussing this to illustrate the properties of our Euclidean plane later on in this playlist of analytical approaches to modern geometry. So we'll be using this as we move forward. We'll have to prove one of its property to be used later on before we try to look for some examples. Thank you very much for watching.